Okay, so in this video we are going to discuss about the energy in the simple harmonic oscillator. So let us begin with the equation of motion of simple harmonic oscillation. So the equation of motion of simple harmonic oscillation was x double dot plus omega squared times x equals 0. Alternatively, we can write this down as kx double dot plus mx equals 0, because we already defined omega squared to be equal to k over m. Okay, now what is the kinetic energy stored in this oscillator? Well, the kinetic energy is half mv squared, right? So we need to know the velocity of the oscillator. So we can express the velocity of the oscillator as x dot, right? So the kinetic energy will be equal to we represent that with k. Okay, so it will be equal to half m v squared, or alternatively x dot squared. Okay, now let's come to the potential energy of the simple harmonic oscillator. Well, we derived the form of potential energy, right? And it was half k x squared, right? Now how do you get this thing? Well, as you know, there is a relationship between force and this potential energy, right? That relationship was force is defined as minus ddx of the potential energy in one dimension, right? For any conservative force. So from here you can see that potential energy is minus integration of f dx, right? And in case of a simple harmonic oscillator, we know that the force is minus kx. This is the restoring force, right? So the potential energy will be equal to minus integration of minus kx dx. Now if you integrate this thing with proper limit, let's say we from zero position, the equilibrium position, we get to some distance, say x. So then if you integrate it out, you should simply get half k x squared. Okay, so this is how we get this potential energy term. Okay, all right, now what is then the total energy? Well, the total energy then will be equal to the sum of the kinetic energy plus the potential energy, right? Okay, so we can put these things here, right? So here is mx dot squared plus half k x squared. These are the things. Now what is this x? Well, we know this x varies with time, right? And by solving this equation of motion of simple harmonic oscillation, we know that x can be written in this form: a cosine of omega t plus phi, where again we know that this a is the amplitude of the oscillator, phi is the phase lag, and omega is the angular frequency, right? And again, this omega was defined to be square root of k over m, as we mentioned here as well. So now if we put this thing here, and we need to know x dot, so let's find out what x dot is. So x dot will be a sine differentiating with respect to t will give us cosine of omega t plus phi, again with an extra omega in front, right? So let's put these values in this equation. So what do we get? We get half m x dot squared, so that means omega squared a squared sine omega t plus phi is squared. plus if we put this value here, we get half k a squared cos omega t plus phi squared. Okay, so we get this equation as the total energy, and we see how this varies with time, right? Because we have time in this expression. Now if we simplify this thing a little, as you can see that we can write down omega to be equal to square root of k over m. So omega squared is simply k over m. So if we put k over m here, we get this m and m cancels out, so we simply have k, right? So that is, this expression again actually gives us this thing actually gives us k. Okay, so as we see, we can take this thing common, right? Half k a squared, and we are left with this sine squared omega t plus phi plus cosine squared omega t plus phi. Okay, now as you can see, this is equal to 1, right? So we have the total energy equal to half k a squared. Okay, so this is the total energy, but you can see that there is no time. That means it is not dependent on time. So the total energy is constant for a simple harmonic oscillator. Okay, and this is equal to half k a squared. Now, what is this k? Well, this is the spring constant, okay, if we consider a spring mass system. So if we have a spring with higher k, that means it stores larger energy, right? And if we pull it apart a little more, that means if we give it a larger amplitude, it will store more energy. That's what it says, right? Now let's see how kinetic energy and potential energy varies with time. The kinetic energy is this quantity, which is proportional to actually x dot squared. That means it is actually proportional to sine squared term. Okay, and the potential energy is proportional to the cosine squared term. So it will have all the properties, the kinetic energy will have all the properties of sine squared function, and the potential energy will have all the properties of cosine squared function. Now, as you can see, if cosine of something is small, then sine of something will be larger, so that the total energy will remain half k a squared. Okay, so say for instance, if cosine of say some angle 0 is here, so it will be 1, right? So then the sine part will be 0, so that the total energy again remains k a squared. So that means that the kinetic energy converts into the potential energy, and the potential energy then converts into the kinetic energy, and this thing goes on forever in case of an ideal simple harmonic oscillator. When the oscillator comes to the equilibrium position, the potential energy becomes 0, because as you can see, it is dependent on x squared, and at the equilibrium position x is 0. So that means the potential energy at the equilibrium is 0. Then the kinetic energy there will be the total energy, right? So it will be equal to half k a squared. Again, at the highest point or the highest amplitude, the kinetic energy is equal to 0, because the oscillator stops at that point. Okay, so that means the potential energy there will be equal to the total energy, half k squared. Now let's visualize how kinetic energy and potential energy of a simple harmonic oscillator are related to each other by using a simulation. So here we have our spring mass system. Okay, now in this spring mass system, this is the equilibrium position. Okay, and let us now stretch this a little. say we want to stretch it 5 centimeters. Okay, so here you see new stretched position. Now if we release this object, it will start to oscillate, right? So let us now run this simulation and let's see how it oscillates. So as you can see, it starts to oscillate, and with time, here, let's pause for a bit. You can see that the position here is varying like this because we considered a cosine function. It starts with the highest amplitude, right, and then follows a cosine curve. The velocity will then follow a sine curve, right, because velocity is just x dot. So if you differentiate this thing with respect to time, you get velocity. So it follows a sine curve. Okay, now again the acceleration, well, if you differentiate sine again, you should get cosine again, but with a minus sign. So here you can see the graph starts from the opposite direction, right, from minus some value. So it again varies like a sine curve, cosine curve, that is. Okay, now what is the potential energy and kinetic energy? Well, we know that potential energy is cosine squared. So you see this is a cosine squared function and this is a sine squared function, the kinetic energy here. Okay, now let's restart the simulation to see how it varies again. So let's reset and rerun the simulation. So you can see how the potential energy varies, how the kinetic energy varies, and position, velocity, and acceleration. Okay, so again let's reset it, and now let's consider the energy graph. Okay, so let's run it again. So as you can see, if we pause at any random time, so here you can see this red line indicates the kinetic potential energy curve. Green line indicates the kinetic energy curve. So at this position of the oscillator, this is the potential energy and this quantity is the kinetic energy. Now if you add these two things, this total kinetic energy and this potential energy, you get this energy, which is the total energy represented by this line. So how to add them? Well, this is the kinetic energy and you have to put the potential energy on top of that. So you see, you will get this point, right? So now let's run the simulator again. So as you can see, it varies. Okay, maybe at the equilibrium, near the equilibrium position, let's try that. Okay, yeah, so you see at the equilibrium position, all we have is this kinetic energy because the potential energy is 0. Okay, now again let's run it, and near the maximum displacement, that is the amplitude, all we have is the potential energy and the kinetic energy is 0, and combinedly they give us the total energy to be this line, which we remember is half Ka squared. Okay, so let us run this simulation again by using a pie chart, how kinetic and potential energy varies. Okay, as you can see, when the line is green, this is kinetic energy and this is potential. So now total is kinetic, now total is potential energy. Okay, and the total energy is half Ka squared.